Okay, so National 5 team, in this quick video, I want to just go through the potential divider, which is section 21 of the booklet. Now, it's essential that you know the voltage rules that I discussed in a previous video. If I have 6 volts in a series circuit, those 6 volts will be shared between the two resistors, or in these cases, lamps. So 5 volts and 1 volt. This could have been, it would have been fine for it to be 3 volts and 3 volts. It could have been 2 volts and 4 volts. It could have been, depending on the nature of these components, it can be any combination that adds to 6 volts. So it could be 2.4 and 3.6. As long as they add to 6, it could be any combination depending on these components. Now, in a parallel circuit, every branch gets the supply voltage, which is why we have our houses wired up the way we do. So moving on to look at potential dividers. Now, the first step is to be able to take a series circuit, and let's just say we've got 6 volts and, I don't know, 2.4 and 3.6. There's no reason at all why we can't rotate that circuit. So if I take my series circuit and I put the series circuit on its side, I can then say, well, that's fine. I've actually flipped the battery around here, which is unfortunate, but and say one of these might be 2.4 volts and one of these might be, and the other one might be 3.6 volts. And of course, these could have been any combination that adds to 6 volts. So what does a potential divider look like? Now, you might be thinking to yourself, what's the point of a potential divider? And the answer is, there is definitely a point, okay? So there is a point, and I'm going to explain to you what it is, basically. It is a circuit where you have 2 resistors in series, like this, and we have 2 voltages, and we're going to use, in later circuits, we're going to take off a voltage and use it as an input voltage to another circuit. So there's an option, which we'll get into later, of saying, okay, off here, we'll take off this voltage, and that will be used in a new circuit doing a new thing. And it'll be important what its voltage is, because we'll feed it into things called transistors. And so it'll be important what it does. So this is us working towards understanding using transistors in control circuits, but this is very much the start of that process. So now what I wanted to explain was that you know a conventional way of finding out V1. And the way that I've always told you was to find out the total resistance. So here I've gone through the process. I've started off and I've found out the total resistance. I just add the 2, total resistance is 12. And then I know that the total voltage is 12. So I can use my Ohm's law to find the current. So I'm going to phase 1, find the total resistance. Phase 2, find the current. Now, if you're not so sure about these Ohm's law calculations, this is section 9. So you could go back to the booklet and review section 9. So moving on, I put in my numbers. I've got 12 volts and I actually have a total resistance of 12. So my current must be 1 ampere. So that's that. Now, I can then for step 3, I can then use the Ohm's law equation for each individual resistor. I now know that each one has got 1 ampere flowing through it. It's a series circuit, so the current is the same everywhere. And so I can say, okay, V1 must equal my current times resistance, which is 1 times by 8. So the voltage here must be 8 volts. And in the same way, V2 must be 1 times by 4. So the voltage must be 4 volts. And so that's fairly straightforward, and it tells us that the 8 and the 4 add up to 12, so that's entirely appropriate. That's as it should be. Now I'm suggesting to you the 3-step way is pretty slow. It works. If you can't think of any other way, it's a way to do it. But it is slow. A quicker way is to use this equation where you say V1 equals the supply voltage times by R1 divided by the total resistance. So just to go through this in my new way, just to go through this particular question in my new way, I just split it up into 2 sections. I'll just cover that bit up for a second and say, okay, my supply voltage is 12 volts. I've got resistance 1 is 8, and the total resistance is 12. And so I do that and I end up with 8 volts, which is what I worked out before, but I've done it in one step using one equation. So that's my suggestion for you. Now, you can, if you're confident you've done that right, you could say, well, the other voltage must just be the supply minus this one, because V1 and V2 add up to the supply. So I've just done, 12 minus 8, 12 minus, if I know this is 8 and I subtract the 12, that must be 4. So I've done the whole thing here in a much more quicker way than doing it in 3 steps. But the 3 steps is not wrong. Okay, so let's have a look at doing another example, a slightly more complicated way. Is this another example? Okay, so I haven't drawn in my voltmeters very well here. I should really draw in my voltmeters more accurately. There we go. Now I've got 20 volts as my supply voltage. I've made an error with the symbol. This should be a dashed line, so apologies for that. And so that should really be like, is what I mean, to be, in case there's any confusion there. That symbol should have been that one. It shouldn't have been a complete line. Okay, so here's the equation we've been looking at using. So my V1 is 6. Sorry, my V1 is not 6. My supply voltage is 20. My resistance for this V1, my resistance is R1. So I'm calling this R1, which is next to V1. R2 is next to V2. And that's 6. And the total resistance is 6 plus 4 is 10. So I substitute in 20 divided by 6. Sorry, multiplied by 6 divided by 10. And that gives me 12 volts. Now I could jump to the conclusion and say, well, if this is 20 and that's 12, this must be 8. Or alternatively, I could do the whole calculation again and I get 8. So it's important that the supply voltage equals these two added up. 8 add to 12 equals 20, and that's a good check to do at the end. Right, so big themes then in these potential dividers, that the bigger resistance has the bigger voltage. And it's important that, just going back to that one, the 6 ohms has actually 1.5 times the voltage of the 4 ohms. And because that has 12 and this has 8. So there we are. Bigger resistance, bigger voltage in a potential divider. So now I would suggest to you that you could, if you can do that, there isn't really any reason why you couldn't move on to section 21 and look at these potential. Now there's an example at the start of section 21, and then you can start at working out some voltages for yourself. So here they've put some resistances in and asked you to work out voltages, okay? But unfortunately, in the kingdom of Google, they haven't got the ohms in. So find the potential difference across each resistor in the following circuit. That seems fine, but in the Google transfer from Apple, they've lost the resistance. The resistor symbol has become a fuse symbol because the straight line shouldn't go through the rectangle. And these should be 4 ohms, 6 ohms, 20 ohms. So there's no reason why you can't work through those, but these are better. For some reason, these have worked out to be working. So maybe at question 13, 14, 15, suddenly we've got the right symbols where we've got proper rectangles. But there we are. So I'd like you to be able to work through that. And it's kind of important, before we go into the next section, I'm going to do another video on how to do this next section. So I'd like you to have a go at section 21 and do some of the questions. And all this is building up to transistors. So our next step will be LDRs and light dependent resistors, and then we'll be moving on to transistors. So if you've understood the video, you should be able to do the section 20 questions on potential divider, section 21 on potential divider circuits.